Good morning, everyone. Today's webinar is on system registers. So this is the second webinar we've done this. So it's more of the built-in system registers that are quite useful in applications. We'll go straight into it. If you have any questions, we can get to those in the end. You can put those in at any time, and we'll get going.
Hello and welcome to today's webinar. Today we're going to be looking at more little known but useful system registers. Let's get started. Let's look at our agenda for today. We'll start by having a quick review of system registers, what they are and what makes them so useful. And then we have 3 overlooked system registers that we're going to cover in today's program. And for each of those we have application examples. There will be demonstrations throughout and we'll finish with a Q&A session. System registers are a built-in type of memory available in every Horner OCS. They handle system status and settings within the unit. System bits and registers can be thought of as counterparts to the parameters in the system menu of a Horner OCS. Whether a system register is read-only or read-write depends on its specific function. We have 2 types of system registers, bit type or type S, and there are around 13 of these, and then the more common word type or type SR, which includes at least 192 registers. Note that the count may vary between units and between logic languages. System register support varies by OCS model and logic language. Before starting a project, we recommend referring to your OCS Units User Manual and reviewing the System Registers chapter to identify the registers available for your project. Each controller has a unique serial number built in, and you can access the system coordinates for the last touched screen area. Now we'll look at 3 specific system registers which are often overlooked but valuable. We'll begin with the system beeper, which is a relatively straightforward feature. The touchscreen beep, which is enabled by default but can be disabled, can be triggered via logic or screen actions using System Register 184. Specifically, the lower bit controls the beeper. When it's set to 1, the beeper activates, and when it's set to 0, the beeper deactivates. So why might you want to trigger the beeper separately? It can serve various purposes. For instance, you can use it to alert operators to new alarm conditions, especially when they are focused on other aspects of the machine. Additionally, it can be useful when an operator is manually loading a part into a fixture. Sometimes, determining if the part is fully loaded or nested can be difficult. In such cases, a simple beep can indicate to the operator that the part is correctly positioned. These are just a few examples of how you can utilize the beeper in your application. Now we'll look at an example. So here on the bench we'll go to the beeper screen, and we have a demonstration here on how we might utilize the beeper. So one thing we did was we connected a push button on the screen that will trigger the beeper. So the longer we hold in that bit, the longer the beeper is on, which means we can have a short beep to do one function and a long beep to do another. We could even do a pattern of beeps if we wanted to. But in this example, we're going to use the part nesting example of providing validation to the operator that a part is nested, and they can continue. So when the limit switch turns on, that indicates that the part is nested. So we're going to give a short beep. So you can tell whenever that switch turns on, we're turning the beeper on for 50 milliseconds or so. And then also, if we have an alarm condition, we're going to execute a long beep. With the long beep, the idea is for the operator to check out the screen and see that we have a motor load condition or a part jammed or a similar issue. So there's a couple of examples of how you can utilize the system beeper through system registers to maybe call attention to some conditions on a machine to the operator. So now we'll look at this on Cscape. The first thing we had to do was map the beeper system register right here as SR184. We need to map that over to a variable, and we're using variable-based advanced ladder. So we created a variable called beeper, which is Boolean, and we map that over to SR184. So every time the beeper turns on, SR84 turns on. So how would we use this in our program? Well, we created a coil called beeper, and then we have 3 different ways we can turn that beeper on, which effectively turns on SR184. We have a long beep, we have a short beep, and then there's a beeper test from just that push button on the touch screen. So you could do the rest of this logic any way you choose. We said if we have an alarm condition, we're going to detect that we have a new alarm condition and we want to turn on the long beep variable. And then that variable will be on for about a second and it'll turn back off again. So that's the long beep that we are going to have occur whenever we have an alarm condition. And then we also programmed in a short beep so that when the part became nested, we initiated a short beep that lasts for 50 milliseconds or so. So when that turns on, the short beep contact here turns the beeper on. So that's what we did. The key point here is mapping SR184 over to our own variable and program. So one more thing we'll look at with regards to the beeper is that in our application we want to turn off the beeping that happens whenever we press the touchscreen, so that the only beeping that comes out of the unit would be something we want to alert the operator to. So we also mapped a variable to SR183, and that is a system register that when it's on, it causes a beep to happen in every key press on the touchscreen. And when it's off, it prevents a beep happening from every press on the touchscreen. So we put some logic in with an always off contact, making sure that SR183 through this variable is always off. That way, when the operator hears a beep, he knows it's either an alarm condition or his part is nested or something more intentional like that. Now we'll move on to the second overlooked system register, which is the ability to create or load clones. For those unfamiliar with cloning in the OCS, the Make Clone feature allows you to save the program, OCS system settings, and variable values to a micro SD card stored in 2 files. So why might you want to do this? Imagine you have a machine with various parameter setups and configurations that change over time. Having a clone stored on micro SD ensures that if you ever need to replace the controller or encounter another issue, you can quickly recover your fully configured and operational machine. However, granting access to the system menu for making a clone might be risky, especially for operators or inexperienced maintenance personnel. To eliminate this risk, you can create user-friendly screens in your application or trigger the clone creation directly in your logic. This approach provides more control and reduces the chance of accidental errors when making a clone. So how can we create a clone by manipulating the system registers? We have 4 bits to either manipulate or monitor, and we'll begin with the make clone bit, or SR164.9. When we set this bit, it initiates the cloning process. As soon as it starts, the operator's screen switches to the clone screen in the system menu. When the clone is complete, the bit is cleared and the screen returns to its previous state. We can also monitor another bit, SR164.11, which signals if there's an issue during cloning. If there's a problem, it indicates that the clone didn't execute completely, likely due to a missing memory card in the unit or its removal. This is the process for creating a clone. Now we'll discuss the reverse process, restoring or loading a clone. How can you do that? It's achieved by turning on and leaving on a different system bit, SR 164.10. When this bit is activated, it triggers the loading of the clone. In other words, the program is loaded from the memory card. Since this is part of the normal clone creation process, once the program is loaded, the unit will reboot. After rebooting, the OCS will display its initial screen. This summarizes the process of loading a clone. Now we'll go to the bench and look at executing this with the demo program there. So we'll go to our next screen, and here we've created some buttons to show how this could work. We've labelled the Make Clone button Backup Machine, so this bit is actually tied directly to that specific system register bit which initiates the Make Clone. And then this is an indicator that we have the ability to reset from the screen. That tells us if the backup fails. So now we'll see if we can initiate a Make Clone, which we're calling Backup Machine here. So first we pull the memory card so that when we back up the machine, after briefly going to the system menu, the backup immediately failed. So we clear that error here and correct the issue by plugging in the memory card. And then this time when we press Backup Machine, we go to the clone screen and the Make Clone is executing. And then when it's done, we go back to the screen we were on before, and because the failed bit is not on, we know that everything is working well. And then similarly, if we want to restore the machine from a memory backup, we could do that from the screen here as well. So this restore bit is tied directly to that load clone system register bit. So again, if we pull the memory card and press restore machine, it immediately fails. We would clear that error if we choose to, or we can just correct the issue by putting the memory card in and trying again. And this time we load the new program from the memory card, and then almost immediately, as soon as that is done, we go through the rebooting process, which is the normal part of the load clone. So that is load to the new program, then reboot to load all the system settings and all the system variable values. So then we end up on the initial screen for the OCS. Now this demo didn't require any logic at all. It really just required the mapping of variables. For push buttons and indicators that are on the screen to the specific system registers that we're talking about there for Make Clone and Load Clone, as well as the indicators that let you know when they fail. However, there is some ladder you could choose to add to your system. If you want to automatically make a clone at the end of every day, which is certainly something you could choose to do. That way, if you ever had to replace your controller, the worst case scenario is that you'd be picking up where you left off 24 hours ago. To configure that, you'd simply utilize a time of day function block here. So the way we've configured it is every day at 23:59 we kick off a one shot. Now that one shot is not directly used to write to SR 164.9 for instance, but it does actually trigger indirectly SR 164.9. So we set that make clone bit and then let the whole process work itself out. And then the firmware itself will clear the clone bit just like we demonstrated. So if you choose to create a clone every night at 11:59, that's how you would do it. Now we'll discuss the final one on our list, the free running timer. Besides the free running timer that's included in every timer added to your program in Cscape, there's also a free running timer stored in the system registers. Specifically, this can be found in SOR 149 and 150. It's an unsigned double integer value that counts up in 10 millisecond increments. It continuously counts and there's no way to reset it. The counting happens between a value of 0 and a very large number, starting with 4 billion or more. This timer continually increments, and with a little mathematical manipulation, you can use it to effectively time events in your program. So now we look at how we might utilize that on the bench. So we'll go to the free running timer screen, and here you can see we're displaying the value of that system register 149 here on the screen. So what we have is an unsigned double integer value that's just counting up, and it'll eventually find its way all the way past 4 billion, and then it will roll over. And in this example, we're using it to time the cycle of the machine. So we could have added our own timers and counters to the logic, but instead we chose to utilize the free running timer and a move command and a small bit of maths to do the calculation instead. So we have input number 8 connected here as the cycle. So we'll turn the cycle on and then off again, and you'll see a new reading come in for the new cycle calculation. So every time we complete a cycle, we're utilizing the current value of the free running timer, subtracting off the value when we started, and then coming up with the result. So you can use this free running timer for a whole variety of different functions, both functions that are really short in duration and also ones that are longer. Now, one thing we'll mention here is that the free running timer is just like any other timer in that its value inside your logic program is going to be read and fixed at the top of the scan. The free running timer is a fixed value, and the next time you get to the top of the scan, it will have incremented. So it's not faster or more accurate than the high-speed counter functionality that's built into every OCS, because the high-speed counter functionality is not scan dependent. It's got dedicated silicone that is measuring time differences between inputs, so it's going to have higher resolution and more accuracy than what we can do for a scan dependent scenario, but still, the free running timer can be extremely useful. So what logic was required for this free running timer? Like everything else, we start out by mapping a variable to the appropriate system register, which in this case is SOR 149 as an unsigned double integer. And then for the demonstration where we were basically timing the machine cycle, we have a variable called machine cycle that's tied directly to %i8. So when that turns on, we're going to trigger a one-shot bit, and when that turns off, we're going to trigger a different one-shot bit. So when we turn on, we store away the current value of the free running timer in a double integer variable. And then when our cycle input turns off, it means we're at the end of the cycle. So at that stage, as long as our free running timer value is larger than the value, we store it away. It's just a simple subtraction to get our cycle time. Now there is one other case we have to account for, and that is if by chance while we were timing, our free running timer rolled over, because in that case, the free running time or value when we're done with the cycle will not be greater than the one we stored away. So in that case, we have to do some slightly different maths to find the difference between the maximum value and the value we stored away, and add that to the current value of the free running timer. So the free running timer can be highly useful and without a lot of logic required. That concludes our discussion on the 3 system registers we wanted to demonstrate today. Remember, whether they're %s type or SOR type, system registers represent the OCS status and can sometimes be written to for affecting its operation or setup. There are numerous system registers available, typically numbering in the hundreds in most OCS units, and many of them can prove quite useful in various applications. However, the specific system registers supported can vary by model, so consult your user's manual for your particular model. In this session, we've highlighted using system registers to control the beeper, create and load clones, and utilise the free running timer. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so nice and straightforward one today. I don't see any questions in. We are taking a gap next week, so we'll be back in 2 weeks with a webinar on user access. So if that's of interest to you, you can head over to the website, to the webinar page, and the registration link will be there. Okay, thank you very much. I think that's it for today. We'll see you all again.